Well, I think we'll begin. Good afternoon. My name is Gary Baldwin. I'm the Director of Special Projects for Energy and Citrus and the Managing Director for i4Energy, which is the center that sponsors this seminar series. So welcome to all of you once again. Our apologies to the studio audience here because we don't have our regular venue in the auditorium. We're a little cramped today, so there are seats outside for those who were not able to get here earlier. And welcome to those viewing us on the internet, especially our sister campuses and our colleagues at LBNL. Today we're very honored to have Professor Marija Ilić from Carnegie Mellon University in Pittsburgh, where she is a professor of electrical engineering and engineering and public policy departments. She received her doctorate from Washington University in St. Louis. She has more than 30 years of experience in teaching and research in the area of electrical power, system modeling, and control. Her main interest these days is in the systems aspects of operations, planning, and economics of the electric power industry. She's co-authored several books in the field of interest. She is a fellow of the IEEE, and we are very pleased that you're here with us today. Thank you very much. So you put that on. And unfortunately, you just have to push the advance. I forgot to thank the California Institute for Energy and Environment for these, for supporting this series and for these lovely lunches that are being served. So my colleague Damon Yeague, thank you very much, Damon.
Thank you.
And Carl, if you're listening.
Good afternoon. Thank you for coming. So as you heard, I've been one of the very few who sort of persevered through the years of electric power systems when nobody cared about it. So I'm very happy to see, I was at a couple of other schools here on the West Coast, and I'm really happy to see that there are students, interested in this field and that things are getting more exciting. So I want to share with you some of the things that we are doing at CMU in this area. By the end, I hope to convey to you a possible framework for adjusting the way things operate today so that you integrate a lot of renewables and demand-side response in an efficient and reliable way or in a sustainable way. So we'll see. Please feel free to ask any questions that you may have as we go. I want to just acknowledge that this work is happening at our Electric Energy Systems group at CMU. And I want to start by taking a step back and clarifying what we mean by sustainability. We don't mean necessarily just environmentally. Oh, sorry. The first is the quick outline. I want to clarify the attributes of sustainability, multiple attributes of sustainability rather than just thinking about the environment, and to make the case that in order to make the system sustainable short term or to induce the system to evolve into something that's sustainable over a long period of time, one needs functions that today's operating utilities don't have, things like just in time, just in place, just in context, and a lot of IT-enabled automation. So in order to make that case, I want to first very briefly show a few pictures on what is changing on the system, what the system is like now, primarily from the IT point of view, and then to talk about something that we call at CMU Dynamic Monitoring Decision System. It's basically a cyber system overlaid on the top of physical system, interacting with the physical system, which actually supports sustainable functions. And illustrate that on a sort of toy example of what does that mean if you were to integrate a lot of variable wind energy with the demand-side response, etc. And one thing that I've been preaching about for years, and Praveen is here, he's been doing that also for years on and off in power area, right? That it's really not, if you just think about these problems from the component point of view, that's not good enough. The system aspects of the problem are very important. So to start with, we want to just talk for a minute about what we mean by sustainability. So when you talk to power engineers, they talk about the system being viable. This means there is enough supply to meet demand unconditionally during normal conditions when everything is in operation. There is a variation of that when you have a large component failing, large generator failing, large transmission line having forced outage. Power engineers talk about that as the system having to be reliable. It means you supply customers, let's say, for at least 30 minutes. You should have enough reserve, and the system should be designed in the right way. So you supply the customers unconditionally for another 30 minutes, even if you have one failure on the system. That's what's referred to. So the first two attributes are really engineering attributes. That's what power engineers worry about. More recently, with the push for sustainability, there has been a lot of effort to now relate these functions, basic functions of the system, to making the system also more efficient in terms of short-term efficiency and also long-term efficiency, so that you don't have underutilization of the capital investment and so forth. This is what many people think about sustainability as the only attribute. And we work a lot with, and I'm sure people at Berkeley here work a lot with new technology players in the field, and those people really worry about business sustainability. If I put something on the system, is it going to pay off so that next time around, the next plant can come on and so forth. So this is for us, basically, that is a multi-attribute notion rather than just one single notion of clean. And as I said before, we want to make the case that in order to make one physical system have these attributes and very good trade-offs between these attributes, you would have to have these new functionalities that I mentioned. Just from the very basic objective point of view, what the way things are done now in the industry, all the software in the control center that you have at the utility level, they solve the problem this way. And it is our belief that in order to make the system sustainable, you would have to transfer the system, the objectives and the practices into something else. So right now, basically, you have one single optimization, supply meeting the demand, unconditionally the demand, subject to everything else being a constraint. In other words, given the tariff, you have to recover the cost, given a predefined CO2 constraint, etc. What this means is that you optimize the short-run generation cost. You use the cheapest power plants first, subject to transmission congestion, etc. But then everything else becomes an externality to that energy. So if you think about that from the economics point of view, that's public good. From there on, all the incentives get mixed up. And so this is part of the problem, because this is how ISO clears, the bids for generation and demand. So basically, there is no clear way right now to say that somebody who is polluting more should be paying more than the others. But mathematically, one way to think about it is to say that this is because the problem is posed that way. If one can have an environment in which you actually have reconciling trade-offs, for example, this is the simple one, and at the market level, it's beginning to work, at least up to one point this way. So you don't schedule the cheapest generation to meet demand unconditionally. Instead of that, there is a demand function for willingness of customers to pay for that generation. So you have multiple trade-offs between the generation cost and the willingness to pay for consumed power. So there are two decision variables. How much you consume and how much you produce, rather than unconditionally consume. And the same thing goes for all the other attributes. So the minute one poses the problem this way, one can begin to think about electric energy provision as a multi-attribute product, multi-product that gets bundled one way or the other. So you can have, energy at value with the environmental characteristics bundled into one type of product, or if you don't worry about environmental, it's just energy, etc. And that has huge implications on, who pays for what and on incentives. But one way or the other, these constraints now become private property. Okay, so in order to think about implementing these, multiple trade-offs and sorting out the signals for who is doing what on the system, I just want to very quickly give some cartoons here for people who don't work with power grids all the time. So let's say this is your high voltage transmission grid with very large generators, and then goes down to, let's say, substations level at the city level. But there is, the way the grid is now, is there is just information exchange, SCADA information exchange between the control center, which is at the utility level, and down to maybe substation level. There is no information exchange from the substation level anywhere down. Okay, and so this is sort of fundamental problem that needs to be solved, in the sense that, you know, how are you going to, if these people are responsive, how are you going to account for that and schedule them the right way? So customers are diverse, but they are not actively participating because there is no active information exchange. And consequently, all what utilities do, in a nutshell, they basically forecast the system demand at the system level, and then schedule generation on and off for anticipated system demand. There is no feedback for demand. So you schedule units on and off using so-called unit commitment programs. And once the power plants are on, then as you know a little bit more about what the accuracy of the forecast is at the system level, then you adjust the outputs, and that's what's known as the economic dispatch. It's important to keep in mind that this is done statically. You know, adjust it for next 15 minutes, forgetting about what happened before, et cetera. So it's just least square optimization over and over again. So the trends are not taken into consideration. And this is going to be important for what we talk about in the consequently, if you want to think now about integrating wind, for example, this is the forecast demand system level, which is fairly smooth. And then you have very variable wind. So there is a net demand, which is basically system demand minus wind, because wind is negative load. And if you treat wind as negative load, everything is very, very variable. And then if you were to apply the same scheduling practices as I summarized, then you would have to have very fast responding units like natural gas following up and down all the time these variations. And that's sort of dirty. Yes?
Is there hours on the horizontal axis?
Sorry?
The horizontal axis is hours? Is that
this is hours, yeah. Actually, I think this can be either day or, you know, there are different periodicities. For everything, this is just sort of for illustration purposes, but you can work with actual numbers. But the point being that combination of smooth prediction of system demand with very variable wind is going to give you system-wide level a net load, which system operator sees as something very varying, and then they need to schedule very fast responding units, which is fast, is expensive, and actually pollutes more if you turn your plants on and off all the time. Okay, so this is the way it is now. So what is changing in a nutshell? There is a lot of talking about deploying AMIs and different things and distributed resources. So basically, remember the distribution level where we don't have communication. That's where we are putting technology for responsive demand. There are variable resources, including photovoltaics, PHEVs, et cetera. They are coming up, geothermal. They're all on the lower level. And in addition, we have more of objectives for cybersecurity and environmental constraints. So this is a huge change that requires now, what's causing for the operator is the problem of having a much harder time to predict the total supply-demand imbalance. And I want to argue that without the self-commitment by the distributed resources and load-serving entities, this problem cannot be done in an efficient way. So the problem of having different actions by different groups of responsive demand without correlating those is going to be very inefficient. So how to correlate them to aggregation, and what information the system operator needs to know in order to actually ultimately just schedule very little of large-scale generation to supply that last imbalance that doesn't get supplied by these distributed resources. In a nutshell, transmission system, control center can no longer assume that distribution load is constant or predictable, because you have to take that feedback into consideration. Okay, so in terms of changes of the physical system, all these in blue were the existing physical devices, and now you have different things. You have a smart house, you have photovoltaics, you have PHEV fleets. This is coming on. This is all what a lot of people are thinking about as a smart grid, but it is really here at the lower voltage levels, right? And then what we are suggesting is that it's absolutely critical to rethink the information exchange across from end-to-end information exchange from the smallest customers all the way to the control center in order to capture potential benefits from these distributed resources. That's what we call, we have this initiative, the consortium that I've started, Dynamic Monitoring Decision Systems. That would be basically a transformed SCADA that enables those interactions. So what it would mean would be that instead of stopping here, where you have these in blue dotted lines, the information exchange, existing one, there has to be some information exchange between all the way down to the small customers and from the higher levels to the lower and from the lower to higher up. So it's a sort of multi-directional. A lot of people arguing should be just bottom up. A lot of people arguing should be top down. But from whichever side you look, actually, it's not going to, because it is impossible to predict what's happening on the system level without having this information. Another way around, you cannot decide what to do here unless you know what the need is going to be for your resources. It has to be multi-directional. And I want to go and explain that a little bit more, an example. So one way to do this, is there a question? No? Okay. Okay, so what's happening now? So we are saying this is happening, and a lot of people are working on it. Half of California is working on embedding this intelligence at the user level. This can be data center, can be green factory, can be smart household, automated, part automated, but it's at all levels. We have some embedded intelligence that's coming up. And so that's at the distributed level. And then somehow that embedded intelligence has to communicate with the system in a sort of bottom-up way in order to understand what are the potential benefits of these technologies to the system operator. Another way around, there has to be some economic signal or some other type of incentive which is going to tell these people that the technology they are bringing on board actually has some value and it could recover its cost. So the system like this would basically then merge more into value-based. So if you have a technology which has the value to the system, if everything is done right, that value would actually be communicated back, and that technology recovers its cost faster, and more of that technology comes on, and so forth. So you don't really bias the technology. You don't say, I just want to have such and such. The technology sort of evolves over time, given these signals. Okay, so what does that mean on the actual system? So one way to think about now is, okay, so I have a load. Here is where there was a glitch in the conversion. Doesn't matter. So there was here a scale saying, am I going to have expensive, doesn't matter. Am I going to have expensive large-scale generation, or the load is going to balance the system? So in order to do that, we are saying that you no longer can have this dispatch just from by the control center, assuming what all the resources are doing. You have to have look-ahead dispatch by different distributed resources, communicating that information bottom-up, and then also you have active load management, which is not direct load control, and I'm going to draw the difference there. So for people with control and so forth, there is a lot of distributed model predictive control embedded at the distributed players level, and it doesn't matter if it is demand side or distributed energy resource. Based on the optimization, look-ahead optimization, distributed unit commitment, the willingness to to produce power and send it into the grid, or willingness to consume at certain value, comes as a result of the optimization of the distributed model predictive control that I want to introduce. Okay, so basic idea of the new architecture would be to have a lot of self-dispatch at the distributed resources minimally coordinated. And the whole group is working, depending on which technology you're talking about. At CMU, we're working on what information needs to be exchanged, how to optimize, like if you have demand, what is the demand, what is the intelligence that you have to embed at the demand side, how to aggregate, et cetera, how many layers of aggregation you should have, et cetera. But basically, in a nutshell, different technologies perform look-ahead decision-making, and they take into consideration, it is at that level that they would take into consideration their unique characteristics. Where are they located? What are their temporal constraints, and so forth, how fast they can react. And as a result of that optimization, which takes into consideration intertemporal dependencies, they create bids which are static. And those bids are communicated now to the control center, and where the system operator, at least in the first generation, I would say, of an implementation like this, you can still use the same static economic dispatch once you internalize the intertemporal constraints and the value of the intertemporal constraints at the distributed level. Okay, so I want to illustrate that. Yes?
How often would these bids be done? Every 15 minutes, every hour?
Let me go through an example, yes. But, oh my God, I think that we had a glitch here. Okay, doesn't matter. They didn't convert from Mac to. Okay, so what is here is basically sort of model predictive decision-making process in which distributed resource looks, let's say, over some longer period of time, and optimizes for the anticipated information up from top, let's say, for the anticipated price. They optimize their own, either profit or benefit, and they basically solve distributed unit commitment problem and get, let's say, if this is 24 hours, let's say if you want to go on hourly basis, you would get 24 bid curves, right, which are static now. They're not temporally correlated anymore by the time you solve them. And that actually is the trick that makes it feasible at the system-wide level. Otherwise, imagine you have, let's say, millions of these guys doing it. The system operator doesn't know all the characteristics, cannot schedule them all as one single dynamic programming optimization. First of all, they don't have nitty-gritty information about your house, nor you can optimize over many players in a sort of numerically effective way. I think Shmuel has written many papers on centralized unit commitment versus distributed unit commitment. When the restructuring took place, you end up having a very insensitive optimum. So you can take different combinations of different technologies, still end up in the same system-wide optimum, and so you basically bias technologies, etc. So instead of doing that,
we're going to take a 30-second technical break here, okay, because it's showing fine on my computer, and we're going to switch computers. This is unprecedented in the history of the I4E seminar series. You are witnessing history in the making.
Sorry.
In the future, you run QuickTime, you work QuickTime on your machine, and that's why it'll come up.
Right, yeah.
So get rid of this old dog.
Okay.
And go
sorry.
with the new kid on the block.
All right, sorry.
And let me see.
One before. Yes, okay. Sorry. So this is really what I was drawing here. Basically, if you are demand side, and you want to decide how much to schedule for which hour over the next 24 hours, you know what your load profile internally is, you know what temperature you want to maintain and so forth, so you do your own optimization. And out of that, and if you know about model predictive control, you optimize in a look-ahead way, but you just implement, one thing at a time. And that smooths out the process, so you no longer have these things going up and down, like people are worried about if you have demand-side response, everybody's going to go up, everybody's going to go down. If you have look-ahead dispatch, self-dispatch, then that problem sort of goes away. All right. Or mathematically, let me just try to do this in a few minutes. What it means is basically the system operator, there is some predicted price of electricity for the next step. If this is wind, this is very interesting. Wind would predict, based on its own site and location, would predict what is the maximum power that he can produce for the next step. And the idea is here that even wind, doesn't matter that it's clean, should not be sent fully into the grid. That's not optimal for the system. So basically, the wind power plant optimizes its own profit optimization for an anticipated price over the next 24 hours, and out comes with what's known as the supply curve, which is a function of the power that they want to produce and the anticipated price. And this is the information that goes bottom up from the distributed resource to the either aggregator, or from the aggregator further to the system operator and the wholesale market. And there is nothing different about demand side. The same way, demand knows, let's say, I'll show you an example in terms of math. This is the limit on the temperature that you want to have in your house. That's your physical state variable, between 68 degrees and 72 degrees. Then you perform this look-ahead optimization to optimize your benefit for the anticipated price, and out comes the bid function, which is now static. It's not intertemporal anymore. And that's given to ISO or to whoever is clearing the bids. The state of the art now is, as I said, that here clearing is static. And rather than thinking about redoing this big way and writing a very huge unit commitment problem for all these resources, you're still going to do your static economic dispatch, but the intertemporal stuff is going to be taken here into consideration at the distributed level. And so several students are working on different things. So if we have, I'll show you some more cartoons on this, but out of this distributed look-ahead self-dispatch, you get basically bid curve for different technologies. The one that's interesting is the PHEV, because PHEV can be supply mode or demand mode. So you actually have two pieces here. This is your bid function for PHEV. If you are in elastic demand, this is sort of typical. I'm going to pay anything to get whatever I want. So and if it's elastic demand, that's that. But this is what usually system operator looks for. These are static. They don't really take into consideration the intertemporal stuff. And this is marginal, and this is the price of the conventional power plant. Okay, so let me show you how is this obtained and how is it very different than what utilities are talking about now and trying to claim that they're actually doing demand-side response. So basically, instead of doing direct load control, we are talking about adaptive load management, which means you have to first, at this distributed decision-making level, take into consideration your various preferences, et cetera, and create the bids. That's the information which differentiates me as a load from somebody else. That information gets given to the load aggregators, or who also have, we don't have too much time to talk about them now, but they have huge value in aggregating different resources and making portfolio and for risk management. And that is extremely different concept than what utilities are doing now. They are basically saying you have this agreement, like for the next year, your price is going to be lower if you get interrupted so many times. I can interrupt you any time. So regardless of what is that interruption worth to me, at that time, I get interrupted. And there is really not much of access to market information to the end users. Presumably with the AMIs, this will change a little bit. depending on how they get used. So basically, right now, end users' information is invisible to the system, although we are talking about. So it's a really direct load control rather than something that one can think about as adaptive load management, which is a look-ahead distributed self-dispatch. So for example, you have 10 end users. Each user has different preferences for temperature, optimizes its energy use for the next 24 hours, given either somebody gives to them, or they assume based on the historical information what the hourly varying electricity price is, taking into consideration outdoor weather temperature, etc. And then they, at the distribution level, you basically, what the sort of the basics, the skeleton of this distributed decision-making at the adaptive load demand side is you would minimize the expected cost. This is expected price that you would, as a user, you would have to pay to your load aggregator as time k. This is the quantity of power that you would consume. And this is the cost which is associated with not being within the limits, thermal limits. So there is a trade-off, even at that level, depending on what type of customer you are. And this is very simple example in which this is internal temperature, which changes with some inertia as a function of temperature I have now, and as a function of how much I consume. Okay, so this is what one refers to as the distributed optimization, self-dispatch by adaptive load demand. So it assumes that this information is given from top down or somehow assumed, and then you look ahead, you are time k, you're looking for over time horizon k plus n, and you continue doing this now. In terms of time, can be every 10 minutes, it can be hour, you can have different clocks, and depending on how close you come to real time, there will be different inefficiencies.
I have a question.
Yes.
This might be naive, but this issue of time interval size, you were showing these elastic prices, say, for PHEVs in demand. But a PHEV owner is somewhat inelastic, say, for a 24-hour period. He knows he needs to drive his car and charge his car.
Right.
So he can be elastic for an hour or so, but he can't be elastic for 24 hours.
Right, so he optimizes what he can do at this hour instead of doing it at some other hour. Right, so there is something that he ultimately has to do over all 24 hours. It's almost like moving the load, shifting the load. Now he can decide at which hour he would charge and discharge depending on the signal, on the price.
1 hour to the next, his elasticity curve will change.
I'm getting there. Okay, sorry, Steve. Okay, so this was the interesting part. So basically, I think everybody knows in this room what the demand curve is. Basically, it tells you what is your value to you as a customer of consuming so much power. So I always need at least a little bit, and I'm willing to pay a lot for that, and then sort of decreases from there. But out of this optimization, you can do this. So what I was saying, you have predicted price from top, but actually the price is not going to be the same. So internally, in your gadget, at the load level, you can actually perturb the price a little bit and create a curve. Done. Okay. So you redo your self-dispatch several times and get the demand curve for each hour. And this is what your question was. So Jay White did this. It took a while, but basically you end up with slightly different slopes for demand at different hours. And what it reflects is that I really want my temperature to stay within certain limits, but I'm going to buy power this hour because it's cheaper than the other hour. And this distributed self-dispatch actually does that. An interesting thing is I don't think I have it here, but what can happen is that there are hours when you are willing to actually sell power back. So you become you are not always just a consumer necessarily. If you optimize over 24 hours. But this is what I showed for these hours is just the downward slopes. So this distributed dispatch basically at the end user level gives you this demand function over the next 24 hours. And yes?
I mean, in terms of the previous question, you had this hour-by-hour response.
Mm-hmm.
But if my need, a manufacturing plant or my hybrid thing, I say, I just want so much energy.
Mm-hmm.
Then my demand is really intertemporal.
Yes.
So it's a function of all those prices.
Right.
You cannot draw this little simple curve.
Right. So.
And how in the world do I reveal to you my intertemporal demand?
Right. So I think maybe I wasn't clear then. So this distributed self-dispatch unit commitment is basically optimizing the energy over 24 hours, right? But you are going to consequently, because you know when the price is going to be what, I'm still going to do my job over 24 hours, but I'm going to do it at different portions of the job at different hours depending on the price.
Right, but I mean, they are, nevertheless, my demand is a function of all the prices, not a function of individual prices.
Oh, yeah, absolutely. Sorry. So let me answer the question technical. So there are two things going on from the optimization point of view. One is that we are really decomposing the system-wide optimum, which is one single unit commitment, for everybody, into layers. So there are duality gaps because of that. And here also, there are intertemporal duality gaps. But what we do, basically, you produce this, and you know that you're going to be a little off. So that's and how much you're going to be off, JY is now doing the theory of that. But, technically speaking, is correct. You have to have them intertemporal, but I think you can gain quite a bit. And the question is, we don't know exactly what the duality gap is. Yes?
Follow up on the same thing. Like when you have a company like Better Place now,
Mm-hmm.
wants to take on charging everybody's batteries, perhaps we should start to think of new ways to define demand. That the consumer, instead of saying, I'm willing to consume so much now at this price, she's going to say, I need so many megawatts hour within the next 8 hours, and I don't care how you provide it to me. And that will
Yes.
create a whole new paradigm for characterizing the demand, and you'll have some aggregator that puts it all together and then convey it to the system operator in a more conventional way.
I agree with that 100%. So basically, you can interpret this result of 24-hour optimization as Dancy Warwick likes to talk about energy minutes. You can have energy hours, right, that you commit, and then it's up to you. How do you use them? So I guess the answer to all of those questions is depending on which way you are going to do it. There will be different risks and different inaccuracies and different options for flexibility. So I'm just showing one, but I sort of, the thing that I wanted to emphasize is that unless you have this look ahead at the distributed level, you are just actually, if you don't take those into consideration, then if the system operator just has some funny agreement with you and doesn't know anything, then it's if the information doesn't go from bottom up in some level, then you are going to basically have very inefficient balancing of supply and demand. So this is what we just created, right? And now this is the tough thing that we are just beginning to work on. Somebody raised the question yesterday, so load aggregators, they can be created in a sort of top-down way. Somebody wants to serve so many customers, and they'll charge, and they'll have contracts. Or, I think Felix Wu worked on this many years ago. You can have the cooperation between the customers, and they create their own. Their neighborhoods can create their own clusters of users. And the minute they are large enough, they can directly communicate the aggregate need, and this is so everything about portfolios is that. So we don't know. This is where there is a lot of work that needs to be done. How, depending on the rules and how are how is the aggregation done, you are again going to have different effects on temporal and spatial inefficiency. And in particular, because this is all, you don't know what's going to happen ahead of time, so it's also about risk management. But let me just show you just this very simple thing. So what is the basic optimization goal of this load aggregator? Independent on how it's created, he has to create the bid function on behalf of its customers and still have its own objective function. So, yeah, okay. So he optimizes the cost of what he has to pay to the wholesale market. That cost is the function of price at the wholesale level and the total amount of energy that's consumed by the customers. And this is what he is paid by his customers. So it's basically the difference between what he has to pay minus the revenue that he gets from his customers, subject to we don't take losses into consideration, subject to the constraint that total amount of power consumed by his customer has to be what he buys from the wholesale market. Another optimization. And in this case, he sits in this middle layer. This has to be somehow known and predicted, and there is some agreement. It can be even contractual or whatever between the aggregator and its customers. Doesn't have to even change all the time. It may be simple agreement, depending. So, and the approaching system-wide optimality, assuming that you know everything, would depend on different contractual agreements. But this is the basic objective function of the aggregator. He would basically want to minimize the cost of of paying for energy on behalf of its customers to the wholesale market minus what he gets from the customers for serving them. Okay, what does this mean? Just 2 layers, aggregate customers and wholesale, just for illustration. So this is how power engineers like to look about this problem. So you have basically a system, electric system, and these arrows are loads, and wiggles are different resources. So natural gas, coal, can be farm of photovoltaics, wind. So what we did, we took this standard IEEE test system that people use for reliability and replaced conventional resources by 50% wind capacity. And the question is now what happens, okay? So remember, this is the prediction of the system-wide load based on weather, let's say. And this is now the potential of wind. So, sorry, this is already net demand after you've added how the wind may change. And the optimization problem gets to be very much more dynamic. You have to do some sort of dynamic dispatch. So what we found interesting, there are 2 things. If you do conventional dispatch, then there are no trends. You know, the power plant, the coal plant is just going to be either on or off or at a certain level, but it's not going to slope in between. You're not going to take the trend because you're not looking ahead. So for typical coal plant, you would get this with the conventional dispatch, or for the other coal plant, that. Or if you start doing things like this, centralized predictive dispatch, that means full-blown unit commitment, taking into consideration, I should have mentioned that, these ramping rates, this is where things get very intertemporal. You have different ramping rates at which different power plants can respond. Then if you do the unit commitment, which takes into consideration ramping rates, you're going to get this solid red curve. So let's say that's a benchmark. If I do distributed predictive dispatch, what we were saying, you break it into so many static things, then this is how much you're off. Okay. And so is it worthwhile now centralizing everything, or how would people adjust and learn in the future? But this is just an example which says this is through simulations how close you can come for a typical example if you're doing distributed dispatch versus centralized. Okay, so what happens now with this 50% wind capacity? What happens is that as the wind changes, goes up and down, the load automatically goes down, and you have this balancing without anything else. This is the coordinated. If the load is inelastic, right, you have that. If you have elastic demand and wind, then you have this grain curve. Load dips in when there is no wind, And the system sort of self-regulates itself. The importance of that is that if you look at these expensive natural gas power plants, if you don't do predictive thing, then the power plant goes up and down. And so this is without demand response. With the demand response, you have very smooth thing. So this is really, doesn't show, Praveen, right? Okay, sorry. So the solid red line is if I were to dispatch natural gas to follow wind variations, right? And if I have demand side response, the way we described it in adaptive way, respond to wind, then there is only so little left for natural gas to compensate. So wind doesn't have to be dirty. You know, some of my colleagues have written the report saying wind is dirty because these things go up and down all the time, but they really don't have to. Yes?
A question, I can't see the green.
I'm sorry about that, yeah.
It looks like there's a drop of 50% in the demand.
Yes, very large.
How much does the price have to increase to get that 50% drop?
So this is the sort of the elasticity that the student worked out. So if this is how much if the demand changes that much to follow wind, right? The price elasticity is -2 down to minus.
It's got to drop 25%.
Right.
That seems very high.
Yes, absolutely. And I think the answer to that question is there may be many, many small guys responding very little. So this is an aggregating.
They're going to save 5 pennies. They probably don't respond. I mean, I agree. Right? They're going to send 5 cents, small guys.
Yeah?
They may not respond.
Well, I don't really know about the implementation. This is just showing the...
It would be interesting anyway.
We have no...
Those elasticity numbers.
We have no real numbers. I think there is Lawrence Berkeley has a lot of numbers and sort of. We don't have. This is just a hypothetical thing. If you have but one answer is that this doesn't have to be done just by one customer. It can be many, many, right? Okay. Did you say 5 or 10? Okay. I think I'm okay. And these are potential savings. So to answer again your question, if the incentive from the system operator is such so that these potential savings are signal going back, that's the concept, then they may do it. It may not be just 2 cents, which we don't have now, right? Okay. So I think I want to, let me just show one and I'll stop. Somebody was asking about PHEVs. Absolutely the same thing. Nick Rotering did this. So if you have a sort of dumb charging and discharging based on your physical characteristics when you drive, etc., you may end up with a large percent of PHEVs. You may end up, the utility will see very large peak in the system load. Okay, if you do it the way that I just described, is another optimization, knowing your physical constraints, knowing your routes, interdependence with transportation, etc., you don't have to build the next power plant. Utilities have to understand this big way because otherwise there is nothing gained by PHEVs. And for us, Nick drew these things is another information exchange question, So what information you have to exchange, etc. It exactly fits in well. I just want to add one thing, and that is if you didn't have this coordination, right? In other words, if everybody were doing their own dispatch, right? Not exchanging the price from top down, then you would have these oscillations all the time. And the question is, so John Doyle was asking me this question, can you do completely plug and play? I don't know the answer, but it doesn't look, the way we have posed it, you really need some coordination because it reflects the imbalance. Maybe there is not enough time to do the information search for everybody. Okay, so I'm going to stop here. Okay, thank you. Yes.
I would like to use this. So we are now open for questions. I don't know about you, but given all the troubles that have been going on with various kinds of automobiles, I want them to fix some other things first before they start working on this charging, recharging, some real basic stuff like brakes. Do we have questions from here or from the people sitting outside? Yes, please. And try and speak up so that we can capture this off for the web viewers.
So in your self-dispatch, you can go to various depths, all the way down to individual households. each one information flowing both ways. Sort of realistically, in this brave new world, I mean, as a household, I would find it very hard to sort of continually, say, okay, how much does this mean to me? How deep do you think we have to go, and how important are aggregators?
I think that households are important, but this would be an automated action. I don't have to be in the loop. Okay, the thing that is, I have to react to the price. My AMI would give me the price signal, so my thermostat adjusts, but I may have a very simple contract with my aggregator. So there is two different things going on. One is I don't have to decide every minute. I've decided that it's putting this equipment which responds to the price all the time, it's worth to me because for the next year, I would be saving so much money. So the aggregation happens through the contractual levels also. But I just sort of physically speaking, I'm very biased on that a lot of small guys is the same as one large guy. So, I mean.
Other question? Comments? Suggestions? Here we go.
You talked about the PHEVs at the very end there. That curve seemed to indicate only the load side of the PHEV. What about the energy as a buffer, the batteries as a buffer, as suppliers? Was it?
It was both. And we had just had a paper that I can send you that Nick said, you do your entire cycle, what you need to charge and discharge, and it results in net load. So negative generation, the same as load, yeah. Yes?
So you mentioned that those last few slides were based on a standard IEEE model for grid reliability. What's the rough scale of that? Like how many consumers are modeled in that?
So I think this is a good question because all the standard IEEE models, they are not going to give you the information that you're asking. It's sort of the aggregate. Remember when I put that today's wholesale level and down to substations? So that's about it. It's a sort of estimated. This is an equivalence model, or let's say very large area, in which that one load represents New England and whatever.
So many gigawatts.
Many gigawatts, yeah, right.
So a follow-up to that. You mentioned that basically having distributed intelligence and many consumers is necessary to get this kind of aggregate smoothing behavior. So, I mean, I guess this is sort of assuming that there's really large-scale penetration of either AMI or smart software in homes or something like that. But I mean, do you know roughly what sort of penetration you would need in order to get that aggregate smoothing behavior?
We don't have any numbers. This is just sort of proof of concept, And then as Praveen was asking, the elasticity has to be large and so forth. I think the next step is really to have some, people are doing a lot of demos. Rather than just doing pilot demo, do some more simulations with real numbers and then go. Because if you do little demo, that's, again, it's not representative. How do you scale it up?
Let me get one from Professor Sanders back here, and I think using this mic is a lot better. So, Seth, if you would just speak into this, I'll hold it.
All right, thanks, Gary. So I wanted to ask about your view of the aggregator. So the aggregator, you're thinking of as an automated function that also is a profit-maximizing device. So it collects money statically as time goes by. Great.
I don't know if Praveen has something to say to that, I guess.
So I'm going to do the same thing with you, Praveen.
I'll sort of pick up on what Shmuel said and the talk I gave at your workshop. There's a fundamental issue about demand equal to supply, and the problem it's an issue is because of quantity variability, either on the demand side or on the supply side. So there are two approaches, I think. One is you force equality by changing prices. So you depend on suppliers and demanders so you got to get those price signals so that equality is enforced. There's another option, which is and if you do that, then you incur price risk. Right? You don't know whether the price is going to go up 50% or down 20%. And I don't think, that's my personal bias, that people can tolerate such price risks, whether it's businesses or consumers. Another option is to pass on quantity risk, so that I tell you, or you tell me as a supplier, that I'm going to restrict your consumption to 5 days out of the month or 1 hour out of a week or whatever, for which, and that is something where you rely now on elasticity of shifting my demand or shifting your supply. And it seems to me, A, much easier to understand, B, the price risk involved is very, very low, and it's all upfront because the contract I've made a month in advance, and would be far more easy to instrument that don't require automated responses, which will shut off my microwave or turn off my car or stuff like that. And I don't know why, I mean, economists like the price risk business, but it seems to me as engineers, trading or sharing or quantity risk would be much easier to implement and would be far more certain than the price. I mean, we've seen with the, during the deregulation period what kind of price risks were incurred.
We're going to let that be the last question, and therefore this is the last answer.
So the architecture that I drew actually allows for that. In other words, what we are saying is that at aggregator level, you can have a very simple deal between the customers and you as the aggregator. That's where the risk management comes in, either for price or for quantity. But this implementation seems to say that although I have the quantity, there is still a little bit control over which hours, that quantity is utilized depending on the price, in order to come near close to some efficiency. But if you just say utility can do it anytime, then I think you lose that flexibility. Maybe we can talk about that some more. Okay. But, this is just a sort of not saying the intertemporal stuff, and risk management is not included at all. It's just the basic flow.
That was a terrific talk. Thank you very much. I want to thank you also by giving you this extremely rare, near one-of-a-kind citrus bag as a gift of appreciation. Thank you very much.
Thank you very much. How many people have it? Everybody in the room? No?
We made several thousand.
Okay.